Today, I'm going to show you 3 ways to improve the animated flag shader that we created last week. Let's go. Alright, so last week we created this animated flag shader, and I made it really basic and simple for a couple of reasons. Number one, because I wanted it to perform really fast so that you could use it on mobile, for example. And also because I wanted to keep the video a little bit shorter. And a lot of you down in the comments for last week's video said that there were some things that I could improve on this or that I left out. And so this week I decided to make another video and talk about 3 things that we can do to improve this. The first one is pretty simple, pretty basic. Some of you had a hard time with the part of the shader that masks out or that reduces the amount of animation that's happening near the flagpole. So right here you can see I've got my local position, and I use a component mask to get just the x-axis, and then I multiply the offset that's happening by that axis. And what that's doing is it makes the amount of animation that's happening over here where the flag is going to be attached to the flagpole really small. And then the further away from the flagpole that we get, the bigger our flapping waves or wrinkles in the flag are going to be. Now, one piece of important information that I left out is that in order for this masking to work, where there's less animation here where the flag is attaching to the flagpole than there is at the end of the flag, in order for this to work, you need to put the mesh pivot point over here on the side of your mesh. I think some of you were using a flagpole mesh maybe with the pivot point in the middle, and that gives incorrect results because it makes the animation small or less in the middle, and then it gets stronger out toward the edges, which is not what we want. So for your flag mesh, be sure that you put the pivot point on the side where the flag is going to be attaching to the pole. And then also for your flag mesh, you want to make sure that your mesh is tessellated enough or subdivided enough that there are enough triangles. So if I switch from lit here to wireframe, you can see that our mesh has a lot of triangles in it, and that enables us to have enough vertices so that when they offset, the animation is smooth. If I were to cut this down to maybe 1/4 or 1/8 of the number of triangles, it would draw faster, yes, but the animation would end up really chunky looking or edgy. And so when you create a mesh for an animated flag like this, you want to make sure that you have enough triangles. All right, so that's thing number 1. You want to make sure you get your pivot point on the edge and your mesh has enough triangles. Number 2, an issue that we're having here is that if we try to rotate the flag, I'm going to rotate it around this way, and you can see when we do that, it goes flat and it's just kind of doing this weird undulating thing. And the rotation is not giving us the behavior that we expect. So I'm just going to move this back. So when we're rotated like this, it looks great. But when we rotate it 90 degrees, it has some issues. And I imagine if I rotated it down, it would probably also look kind of weird. And the reason that this is happening is because we're bringing in the flag's position in local space, local position, but in Unreal, our world position offset is in world space. And so in order to fix this, what we want to be able to do is rotate our flag around and have this wavy animation stay coherent and still look nice no matter how we're rotating it. So what we're going to do to fix this is I'm going to transform my world position offset here from local space to world space. So I'm just going to right click and type transform. And we're going to add a transform node. And right now the transform node starts out tangent space to world space. That's not quite what we want. So I'm going to pull this open, and we're going to set our source to local space and our destination to world space. And now I'm going to connect up my result here and then connect it to our world position offset. And we'll hit save and take a look at what's going to happen. Yeah, that's probably not what we want to have happening. And so what we need to do is just fix up our multiplier here right now, because we told it to work on the y-axis here. And when we're in local position, we actually need it to work on the z-axis. And so I'm going to set this to 0, and I'm going to set this value to 0.25. And we'll save here and take a look. And now we have our rotation back working correctly. And because we're transforming from local space into world position now, if I rotate my flag around, you can see that now, no matter which direction I rotate it, my ripples are maintaining their correct orientation. I can even rotate it like this if I wanted to, or like this. So I can do all the rotations that I want, and my wind ripples are going to maintain their correct shape because we're doing the vertex offset in local position and then transforming it to world. Okay, the last topic that we're going to go over is normals. So what we're doing here is offsetting our vertices, and when we move our vertices around, it's changing the shape of our flag. But the vertex normals on the surface are staying the same, and that's an issue. So if I switch here from lit, I'm going to go to buffer visualization and show the world normals. You can see that the world normals on our flag are just one solid color. They're flat. One thing that I like to do as a little bit of a strategy to check when my world normals are good and when they need fixing is to take a look at a sphere. So when I've got my buffer visualization set to world normals, what this is doing here is it's using color to represent the direction that the surfaces are facing. I'm going to come down here and show this sphere that I have, and you can see that the different polygons or the different vertices of the sphere are facing all different directions, obviously because the sphere is round. So you can see that the direction that's pointed directly at me, at the camera, is kind of this light green color. And my flag is this solid light green color, which means that the normals are pointed directly in that direction. It's the Y direction. If we look at our little XYZ indicator down here at the bottom, my normals are pointed directly in the Y direction. And I actually need them to deform so that they're pointed in the direction that the surface is going when that deformation happens. So, how do we get this to happen? Well, it's kind of a complicated topic, and there are a lot of different methods to do this. Just to help us visualize things a little bit better, I'm going to make our animation stop so that we have just a static deformation. Instead of time multiplied by -1, I'm just going to pass -1 in here. All right, so if we go back to lit, so for each of the points on the surface here, the points are being offset. And what we need to do in order to figure out which direction the surface is facing is find a slope. It's also called a derivative. So if I take this point right here, for example, in order to figure out which, like the slope of the surface, one way of doing it would be to find another point, like the one right next to it, and subtract the position of one point from the other point to find the slope, and then rotate that vector 90 degrees to figure out which direction the surface is facing. So that's basically the process that I need to do. I need to take the point that I'm currently rendering, find a point right next to it, subtract the position one from the other to get a vector that goes between them, and that gives me a slope. And then I need to rotate that 90 degrees, which will give me the normal of the surface. Now in my case, there's something that's working in my advantage, and that is I'm using sine here for my animation. And the really nice thing about sine is that cosine is the automatic, like built-in derivative of sine. So whenever I'm doing my offset or animation based on sine, it's really easy for me to find the derivative because I can just use the cosine. So what I'm going to do is take the input that I'm passing into my sine node and drag down here and create a cosine node. And this cosine node is going to be the core of what I'm doing, because that is my derivative. Now, I need a normal that's in tangent space because Unreal has on the input or the root node over here, the normal is going to be in tangent space. So what I'm going to do is I'm going to add an append 3 node right here. And in order for this to be in tangent space, I need a tangent space normal. And so a typical flat tangent space normal is going to be 0, 0, 1. Right? So I hope you're following there. I just created 0, 0, 1, which is a tangent space normal. And if I wire this into my normal and hit save, what we're going to see here is that nothing is going to change. Actually, let's switch our visualization mode back to the buffer visualization world normal so we can see what the normals are doing. All right, so we can see they're still flat and going in the Y direction because my tangent space normal is 0, 0, 1, which is a flat tangent space normal. All right, so in order to adjust this normal, all I need to do is take my cosine here and just plug it into the X component of my tangent space normal, and I'll hit save. And immediately you can see that my normal has updated. Now let's check and see if I'm getting correct results. So I've got green, kind of a darker green over here and kind of a peach color over here. So if we zoom out a little bit and look at my sphere, I've got green over here and peach over here, which means I'm getting the opposite result of what I actually wanted. So in order to fix that, all I need to do is add a 1 minus node here to give me the opposite or to invert my cosine. Then I can wire that in and hit save. And what you're going to see is that the results will flip. And now I'm getting peach in the areas where it's pointed toward the X direction and green in the areas where it's pointed in the Y direction. So if I compare that with my sphere again, you can see I've got peach color over here, green color over here, and that's the result I'm getting on my flag too. Great. That's kind of a visual method that I use of checking the data, because when we're working with shaders, we don't actually get to see the numbers, and so we use color to represent what the numbers are. And so I can look at my sphere here and see what the colors should be, and then I can look at my flag and make sure that I'm getting the correct results there. Okay, so if I switch back to the animated version of my flag, now you can see that I'm getting animated vertex normals as well. Now there's still one issue with this, and that is these vertex normals are the same strength over here and over here. There's no fall off. So when I'm adjusting the position of the vertices, I'm doing very little position adjustment over here and a lot over here, because we have this multiply by the X position. So I'm taking the X position and multiplying our animation by that. Well, I can just do the same thing with my cosine result as well. So if I take my X position here and multiply by that, what that's going to do is it's going to tone down my normal adjustment over here next to the flagpole, and it'll be just as strong out here near the edge. So now what you're seeing is there's less normal adjustment over here and more normal adjustment over here at the edge. Okay, now if you want to be mathematically correct, we need to add a normalize node at the end here. And this will give us, like I said, more mathematically correct results. But if you find that you don't see a difference with or without this normalize, you can leave it out if you want better performance. It costs a couple of instructions to throw in a normalize node like this. So if you want things to be nice and clean and accurate, use that. But if you want them to be fast, you may be able to get away with leaving that out. All right, let's switch back from world normal to lit mode again. And there we have our animated flag with properly adjusted normals so that we're getting correct lighting as well as correct position animation on our vertices. Okay, so that was a step that I left out in last week's video. And like I said, the reason that I left that out is one, to make the video shorter, and then two, also, sometimes you don't really need it. If you're seeing the flag from a distance or it's going to be small on the screen, you may be able to get away without actually adjusting the normals, and nobody's going to know the difference, but it'll render faster for you. But if you want your flag to look well lit, or maybe there's a specular highlight on it or something like that, you need to make sure that you recalculate your normal. Now, I've done a little bit of research on recalculating normals, and like I said, there's a bunch of different methods for doing this. And I've left some links down in the description for different methods of doing this. So be sure to check those out. Sometimes when, for example, if you're not using the sine node, you can't get away with something so simple as this. And it takes a little bit more math to recalculate that normal. So be sure to check out those resources that I've linked below for different methods of recalculating normals when you're doing vertex offsets and vertex animation in your shader. Okay, let's switch over to Unity, and I'm going to go over the same kinds of things in that engine. All right, here we are in Unity, and we're going to go over the same three things that we went over in Unreal. So first of all, when you're creating your flag, here we have the flag shader that we created in last week's video. So when you're creating your flag, you want to make sure that you have enough triangles in the flag so that your animation will be smooth. Because if you just have one single quad, for example, you're not going to get a nice wavy motion out of that. So make sure that you have enough triangles, enough vertices in your flag mesh that you can get a smooth motion. Second, you want to make sure that you have your pivot point over here on the side where the flag is going to attach to the flagpole. If you have your pivot point in the middle, it's not going to do you a whole lot of good. So make sure that you have your pivot point over there so that, and the reason for that is because we're actually using the position of that pivot point as a mask. Here in this portion of the shader, we're multiplying that offset value by how far away from that pivot point is, so that we tone down the animation here on this side where the flag attaches to the pole. So this part of the shader here won't work correctly if you have your pivot point somewhere else other than right there on the edge where the flag attaches to the pole. All right, the second issue that people talked about with last week's shader is that when they rotated the flag, it wasn't rotating properly. If I do this in Unity, you can see that it's already rotating properly. I don't have that rotation issue. In Unreal, when you do vertex offsets, the vertex offset is going into the vertex offset that you pass in is in world space. But in Unity, we just pass in the vertex position in object space, and we're already in object space here. We've done our math in object space, and that means that we can rotate our object, and the object will maintain its correct deformation regardless of the rotation. So that second issue there is not one that we really have to worry about in Unity because we've done everything in object space and then we pass the result in object space, and that's what Unity's expecting. So we're all good. So that brings us to the third issue, which is normals. Let's switch over to the rendering debug mode in Unity and take a look at the normals represented as color. I'm going to come here to Analysis, Rendering Debugger, and bring up our little Rendering Debugger window. I can select Material here and Common Material Properties, and the one that we want is Normal. So if we take a look at our scene normals here, you can see that these are scene normals in world space, and so the colors that we're seeing represent the directions that the surfaces are facing. It's most obvious if you look at it at a sphere. So this green color here represents the up direction, and then we have a color like this blue color for blue and green for X and Y, and then kind of this pink peachy color. Anyway, these colors all represent the direction that the surface is facing. And if we come back over here to our flag again, you can see that it's just a solid blue, which indicates that those normals are pointing in one single direction instead of being deformed correctly as the flag verts are being offset. So what we're going to do, just like we did in Unreal, we're going to use a really easy solution, in our case, to offset and correctly recalculate the normals of our vertices. We can do this because, in our case, the method that we're using for offsetting our vertices is a sine wave, and the derivative of a sine is the cosine, so we can just use the cosine node to get that value. Really what we're doing is calculating a slope and then finding the vector that's perpendicular to that slope, and that's our surface normal. But it's really easy when we're using a sine wave because we can just use the cosine. So I'm going to grab this output from this add node here, come on down here, and we're going to add a cosine node. And then we actually want the inverse of this cosine, and so I'm going to add 1 minus here. And if we take a look, now we have this animated pattern that is following the animation that's happening in our flag. So that's what we're going to use to get our normal. And so what we need now is a vector3 node, and we're going to plug this into the x of our vector3. And the y is going to be 0 and the z is going to be 1. So now we've created our normal here. And if we add a preview node, you can see that we have an animated normal. So now I can take this and plug it directly into the vertex normal input. And we're going to go ahead and save. And now that our shader's compiled, you can see that we're getting this nice animated vertex offset. Just to help us out a little bit, I'm going to stop our animation. I'm just going to disconnect our time here so that we can get our flag just stopped in one specific position. And what this will allow us to do is check to make sure that we're getting a correct normal. So I'm looking at this sphere over here. I can see that it's blue on this side and pink on this side. And that's the result that I'm getting here. It's blue here and pink over here. Let's take a look at the other side. If we come around here, so we have an issue here where our normals are pointing the same direction on both sides. So we actually need to correct this in the graph inspector. So I'm going to open a graph inspector and go to graph settings and come down here to double-sided mode. Right now it's just set to enabled, but if I drop this down, I can pick flipped normals. And what this is going to do for us is invert the normal on the opposite side of the flag. So when we're on this side of the flag, we've got normals that are pointing toward us this direction. And when we're on this side of the flag, now we have normals that are pointing toward us in this direction. Okay, so we've correctly calculated our derivative here and created a recalculated normal. And then we've passed that into the vertex normal input on our master stack. And we now have an animated flag. Well, it's not animated yet. Let me hook that back up again. Yeah, and we now have an animated flag with correct normals. Very nice. Okay, so let's switch back to normal rendering view. And you can see that our flag is now lit correctly because the normals are being recalculated in addition to just the position of the vertices. Okay, like I said in the Unity section, there are a lot of different ways to calculate these derivatives and to recalculate the normals. And I linked some resources down in the description if you want to take a look at those. For example, if you're doing some kind of crazy vertex offset where you're not using a sine wave, you won't be able to do this simple cosine shortcut. There's a little bit more complex method for doing that, and those methods are explained in those resources down below. And also, just one last thing, if you're far enough away from your flag or if you want to save some performance, you can leave out this recalculating normals step. If lighting on your flag is not critical, you can save some performance by leaving this out and just keeping the normals flat, if that's something that's not very noticeable. So you'll only want to recalculate your normals if it's something that you can see really carefully. All right, that about wraps it up for us for this week. We took a look at 3 new things that improve and update the appearance of our animated flag. Next week, I think we're going to take a look at a procedural brick shader, or generating a brick pattern procedurally in the shader. Hope you look forward to that and you come back next week. And in the meantime, have a great week, everybody.